Okay. Welcome to the fourth video for IB Astrophysics. We're going to be looking at more about stars' spectrum. Now, we learned in the last video that stars are black bodies and have a particular black body spectrum that has a peak wavelength that we can use to calculate the temperature, and also that the luminosity depends on the fourth power of the temperature. But it turns out the spectrum is even more interesting than that, because what happens is light passes through the outer layers of a star, we call that the corona. Some of it is absorbed by the hydrogen and the helium and other elements, specifically by the electrons in those elements, as it leaves. So what happens is it's a lot like absorption spectroscopy that we talked about in quantum mechanics, where you have the star emits lights at all different frequencies, and then you have a relatively low temperature gas at the outside of the star. And what happens is that particular frequencies are absorbed. And which frequencies those are depends on what elements are present in the gas. And since those frequencies are absorbed, you get dark lines in the spectrum at particular locations where not as much light, where some of the light is absorbed. So if you were to plot the black body spectrum, it might look not like that, but with dips in the intensity at very particular wavelengths. So for instance, hydrogen absorbs at 410 nanometers, 434 nanometers, 486 nanometers, and 656 nanometers, and then various other frequencies in the infrared and ultraviolet. So if you see dark lines at those frequencies, you know that there's a lot of hydrogen in the star, which, of course, we knew about that already. But you can do similar things with other elements and see what besides hydrogen is in the star. Incidentally, this is how helium was discovered. When they were looking at the solar spectrum, they saw absorption lines that didn't correspond to any element that was known in the late 19th century. And so they said, oh, there's a new element in the sun. And they called it helium, because helios for the sun. But you need to know about how absorption spectra work, and that they're used to determine what elements are present in the star. So the chemical makeup. And now we get into something called spectral classes, or the Harvard classification. There are a variety of spectral classes, like for instance, if you look at stars, sometimes they appear blue, sometimes they appear blue-white, sometimes they appear yellowish, like the sun, sometimes they appear orange or red, and then there are even stars that are so dim that they look kind of brown. But it turns out that those spectral classes have to do with the surface temperature of the star. Blue stars have a very, very high surface temperature, while red stars have a low surface temperature. And you'd expect the classes to be in, say, alphabetical order, A, B, C, D, E, F, and so on, but they're not. It's O is the highest temperature, followed by B, A, F, G. Sun is a G-class star, then K, and then M. If you want a mnemonic to remember this, O be a fine girl, kiss me, or Guy if that is your preference. You don't need to worry about the absorption lines that are present in the spectrum. You do need to know the order. You need to know that blue corresponds to very high temperature, and red corresponds to very low temperature. And now we get into the most important classification tool in astronomy, which is called the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram has luminosity on the vertical axis. We'll learn what absolute magnitude is later, but it's related to luminosity. And spectral class, which is a stand-in for temperature, on the horizontal axis. Notice you've got temperature up here in kelvins. Neither axis is linear. The luminosity axis is logarithmic. The temperature axis is just weird. Notice that it's not logarithmic, although it's sort of trying to be logarithmic. And the other thing to notice is that high temperature is actually on the left side of the graph, and low temperature is on the right side. The reason for that is when they first made the Hertzsprung-Russell diagram, they didn't know that spectral class corresponded to temperature, and they just kind of put it in order of color. And you notice that there are 4 basic groups on the diagram. You have what is called the main sequence, which is that long line of stars that goes diagonally across the diagram. 90% of the stars in the sky are in that group. You also have a group of giants. We'll explain why those are called giants, and supergiants above it. And then another group of stars that we call white dwarfs down here at the lower left corner. The main sequence is 90% of the stars. Longest lived stars, there are a lot of them. Typically, we said that earlier that these stars have lifetimes on the order of millions of years on the high end to trillions of years on the low end. Now, as you go this way on the main sequence, you get increasing mass, increasing luminosity, and decreasing lifetime. The stars on this end of the main sequence are very, very small, but last a long time, and they're not very bright. The stars on this end are like rock stars. They're big, they're very bright, and then they die young. And so that is the main sequence. There are also what we call giants and supergiants. These stars have low temperatures, which you can see from the fact that most of them are red. But they have very high luminosity. Now, if we recall, L equals not 4 pi, sigma A t to the 4th. If the temperature is low, which is the case because they're red, but L is very high, what that implies is that the surface area is very large, and these stars are in fact giant. Antares, the example we looked at in the previous video, is an example of a red supergiant. It is around 1,000 times the radius of the sun, so it is huge. And then white dwarfs, which there are quite a few of, but we don't see very many of them. They have very high temperatures, hence they appear white. But they have very low luminosity. And once again, in this equation, if T is large but L is small, that implies that the surface area has to be small, And these white dwarfs have a radius approximately the same as Earth. So by star standards, they are tiny. But they're very, very high temperatures, and so the name is white dwarfs. What you need to know is a description of how we use absorption lines in astronomy. You need to know what the Hertzsprung-Russell diagram is. You need to know what the terms main sequence, red giant, and white dwarf mean, and where to put those on the Hertzsprung-Russell diagram.